So my name is Rutkowska. I work for Cosing in Advanced Marvel Labs, and my talk is about Subverting Vista Kernel for fun and profit. This presentation is based on the research done exclusively for Cosing, and it was first presented 2 weeks ago on a SysCon conference in Singapore. It consists of 2 parts. First part is how to bypass Windows integrity checking for loading kernel drivers into kernel, and the second part is about creating malware which is based on hardware virtualization technology from AMD. Okay, so part 1. So in Vista 64-bit, for the first time, the new policy has been implemented to disallow even administrator to load unsigned drivers into kernel. This was explained as a step towards fighting kernel malware. And for the first time, it was implemented in Beta 2, build 5384. So as for today, officially, it's not possible even for administrator to load any unsigned driver into kernel. This mechanism can be deactivated by 2 legal ways, which were provided for testing. So one way is when user attaches kernel debugger when system boots, and the other one is when user presses F8 when system boots. So this is for testing. There's yet another way to disable this mechanism, but this is only available in beta version. It will not be available in a production version, and this is by editing startup options using BCD edit. Okay, so now we will think about how to bypass this mechanism. First, we should observe that Vista allows, like any other Windows operating system, like XP or 2000, for a user mode application to get access to routed sectors. This is completely legal and documented way. You can read about it in SDK, and just enough to use create file with the arguments you see on the slides. So, like this one, you get access to logical device, and this one, you get access to physical device. I hope you can see the cursor. No? Yeah. Okay. So this allows us to read, well, among other things, to read and write to page file. Page file is something which is used by kernel to page physical memory, which is actually not used to free physical memory for other applications, right? So the code is page to page file. So we have the ability to modify contents of page file by just accessing routed sectors. And this page file it not necessarily does, it just does contain, it may contain code and data from kernel, page from kernel. This sounds very easy, but there are some challenges here. First challenge is how to make sure that the interesting code sections or data sections will actually be paged out into this page file. This is the first challenge. The other challenge is how to find that code which we forced to page out, somehow forced to have paged out, how to make that this code, how to find that code inside page file, which format is unknown for us. Another challenge is how to cause that this code, which we are going to modify, which is in page file, how to cause this code to be loaded into kernel again, and how to make that it will be executed again. And I'm going to tell you how to solve those challenges. Yeah. The first challenge is how to make sure that we actually force kernel to page out into page file interesting code sections. So the easy way for doing this is to just call standard allocating routine like virtual alloc, which again is perfectly documented function in SDK. So when the systems, when some applications, some user mode application starts allocating more and more virtual memory, the system will try to back up this memory with physical memory. And as we will see in the next slide, yeah. I hope you have the copy of slides in your notebook so you can see the slide in a better way than here. But it shows that Okay, this was taken on a test system which had 1 GB of physical memory. I used standard performance monitor to take this picture. So first we have around 1 GB of physical memory available. Then we start allocating memory. In this example, I allocated 500 megabytes of memory. So I asked for 500 of virtual memory, but the system had lots of physical memory left, so it actually backed up all the memory with physical memory. So we noticed that the amount of physical memory dropped down to 500, 600 or whatever. So then was another allocation, second allocation. So the system we're trying to, again, allocate as much physical memory for my virtual memory as possible. And you can see this green line here, and this green line here is the amount of available, the amount of code, the amount of bytes of code of drivers, of kernel drivers, which are in physical memory, right? So number of resident pages, probably pages of kernel drivers. So we see that at the beginning, and by the way, it's a different scale. So the red graph is like 1 GB here, and the green line, this is around 4 megabytes. So there are two different scales. And we see that at some point, when there was not enough physical memory for those allocations made by user mod application, system started paging out kernel code drivers, kernel mod drivers to page file, which we can observe by this green line dropping down here. And by repeating those allocations again, which were made by user mod application, we see that kernel was paging out more and more kernel code drivers until at some point, some like critical point where no more memory from kernel were paged out to page file, and which resulted that subsequent virtual alloc calls were not backed up by physical memory. But this is not a problem for us. The interesting thing is that we can, by issuing a lot of virtual alloc, by calling virtual alloc function for many times, we can make lots of, like we can see, many megabytes of kernel drivers to be paged out. And of course, the question is which drivers or which pageable sections of which drivers will be paged first. Of course, those which are unused, right, are very rarely used. And what could be paged as far as kernel mod is concerned? So first we can have all the pageable sections of kernel mod drivers that can be paged, and the pageable sections are recognized by the fact that the first 4 letters of their names is page. And also we can have data which were allocated from page spool. They can also be paged out to page file. So now we need to find a target which would be a very rarely used driver, which would contain pageable code section, and that code section would contain some function which would be possible for this function to be called from user mod. And I just found one of those one example of a driver like this. It's null.sys. We can have a quick look at in disassembler in this driver, and we will see that it does contain one pageable section. And actually, this pageable section contains driver's dispatch routine, which is very good news for us because driver's dispatch routine can be very easily called from user mod by just issuing create file for the object created by this driver. So we have we still don't, but we believe we have a way to force some of the drivers to be paged out. Now how to find a interesting code in page file. This is easy because we can just do a pattern search. Because if we consider, what we would like to do is we would like to override the first few bytes or few dozens of bytes of the original function of the driver with our shellcode, right? So we can just find this beginning of this function by pattern searching. If we take like the first 64 bytes of the function, there's very, very little probability. In fact, I never experienced like to find something else in a page file. Even though page file can have like many gigabytes, if we search for 64-byte string of opcodes, it's very, very little probability that we find something else than our function. So actually, I already mentioned this. Because in this exemplary driver, null.sys, the function which actually sits in this pageable code section is actually dispatch routine. So it's very easy to make sure it will be called. And automatically, if we can make sure that this function will be called, it means that it will be first loaded from page file. So by modifying this function, so first we make this function to be paged to the page file. We modify it. We override the first bytes with our shellcode. And then we issue create file call for one of the objects created by null.sys. And this automatically causes that kernel will first load that page section, those paged section, into kernel and execute it. This is all we need. So we allocate lots of memory to cause unused drivers to be cause code to be paged. We replace this paged out code with some shellcode, and we ask kernel to call the driver dispatch routine. And this was actually implemented as a one-click program. A special heuristic has been used for actually, because one of the problems is how much memory do we need to allocate so that our null.sys code will be paged out. We cannot actually check, like you cannot check from user mode whether any given code section of any given kernel driver has been paged out or not. So we need to find out a good heuristic for doing that. And this heuristic is based on this graph. We're just trying to find out when this green line becomes flat. So this was implemented as a tool. And the shellcode used in this demo, which was written by Edgar Barbosa, is very simple. It just disables kernel signature check. There's a global variable in kernel which is of course set by those F8 or attaching kernel debugger, which says whether we should do integrity checking or not. So we just put 0 to this variable, which allows for any subsequent unsigned driver to be loaded. Of course, we can imagine many more advanced shellcodes to be used. The sky is the limit here. Okay, the demo. Oh, it's not that one. Sorry. We have a Vista Beta 2. We try to load debug view standard 2 from sysinternals, which is not signed, of course, and we get a message error loading debug view driver because it's not signed. I guess in a few months it will be signed, right? So now we start kernel strike attack. We see allocating lots of memory. Memory was